Research teams in the Netherlands, Sweden, Denmark, and the US are reinventing one of the world's most widely used materials. Each team has found a way to make concrete come alive.
We have invented bioconcrete. That's concrete that heals itself using bacteria.
Across Europe and Asia, engineers are quietly finishing buildings that don't just stand strong. They heal when they're hurt. Tiny cracks that used to spell disaster now close on their own, sealing tight without a drop of glue or a call for repairs.
Self-healing concrete is inspired by nature. A lot of rock formations in nature were formed by bacteria.
It started as one daring experiment in the Netherlands. Now that idea is spreading through hospitals, parking decks, and even water plants. And the secret inside them might be the strangest thing ever mixed into concrete. Inside the world's first self-healing buildings.
If you've ever had to seal a crack in concrete, you know what a pain it can be. But what if concrete could heal itself? Just like skin?
In a small park beside the lakes of Breda in the Netherlands, a lifeguard pavilion quietly started something new. The city needed a small, tough building that could handle spray, heat, cold, and the wear that comes with crowds. The architects answered with a curved concrete shell so thin it looked impossible. What made it special was what happened inside the concrete itself. The outer layer was designed to seal its own hairline cracks, so water would never find a way in. This was no lab test or sample panel. It was a real working building at Gelderse Lakes for first aid and rescue teams, and it became the first real example of a building that could take care of itself.
Research teams in the Netherlands are reinventing one of the world's most widely used materials. Each team has found a way to make concrete come alive.
The choice to use that material on the outside was deliberate. A lakefront building faces harsh treatment. Wind-blown spray, cold nights, hot days, and bumps from visitors. That's where tiny cracks cause the biggest problems, and that's where leaks usually start. So the team applied the special concrete on the roof and walls, not on the inside partitions. From there, the idea spread to places where leaks could endanger people or equipment. In Leiden, one of the Netherlands' largest hospitals reviewed its balconies and found fine cracks on their top surfaces. Each was about 0.008 of an inch wide, yet even openings that small can let water slip in and make the steel inside start to rust. The owners didn't want paint or coatings that would peel or need touch-ups every few years. They chose a transparent treatment meant for that exact type of surface. It was applied across about 21,500 square feet on 7 floors. A 2-person crew handled it in roughly 2 weeks, keeping the same concrete look and stopping moisture before it could travel through the slab.
Harsh environment of concrete, but also to make them produce repair material for the concrete. That is limestone.
That hospital job became a model for how to use the technology in active buildings. A much bigger project came next in Apeldoorn, where a city parking garage needed to keep its lower levels dry. The team focused on the intermediate deck, the surface directly above the equipment and vehicles below. After testing a small section, they treated roughly 129,000 square feet in 2 phases. The top polymer coating stayed in place while crews applied the new layer, and the whole job took days, not months. It became the first large-scale case of self-healing treatment used across an entire garage deck. Another project took the same idea below ground, where water pressure is constant. In Rotterdam, the historic Hulstkamp building added a basement parking level under its foundations. Keeping it dry was critical because the city sits at river level. The team poured about 9,688 square feet of slab and walls, roughly 235 cubic yards of concrete, with a mix designed to close its own fine cracks. A full building self-healing project happened in Japan.
In Shanghai, the World Financial Center is a foundation waiting for a building.
In Sapporo, a new water treatment plant adopted self-sealing concrete across almost every major element: foundations, floors, walls, and tanks. The site covers about 611,000 square feet, and the building itself spans roughly 297,000 square feet. About 6,540 cubic yards of the special concrete were used. The plant includes a tank nearly 23 feet deep, built from precast sections joined on site. Completed between 2021 and 2022, the project proved that an entire utility building, not just one slab, could rely on self-healing properties to hold water where it belongs without extra membrane layers.
See how the process was going, and yes, we were really happy to see that it worked.
The same principle, protect the parts that face the greatest risk, appeared in unexpected places. In Amsterdam, the city's historic Artis Aquarium was rebuilt with 2 upgrades working together. New fiber reinforcement for strength and concrete that seals hairline openings on its own. Behind the scenes of an aquarium, water management is critical. Leaks threaten both the animals and the equipment. By choosing self-sealing concrete for tanks and hidden walls, the team could prevent slow seepage without changing how the place looks. Nearby, a large freight distribution center near Schiphol Airport applied the same thinking to its loading pits. These recessed floors take a daily beating from heavy trucks and constant moisture. They also sit right above service areas that must stay dry. The developer wanted those pits to last longer and require fewer shutdowns, so they specified self-sealing concrete for those exact slabs. Taken together, these buildings form a pattern. Engineers are not coating every wall or floor with high-tech concrete. They are selecting the parts where small cracks turn into costly damage and solving the problem there. So, how does concrete even pull that off? Let's look inside and see what really makes it heal. The secret inside self-healing concrete.
This Dutch invention was the first true self-repairing concrete. This invention marked durable, low maintenance, and climate smart.
A self-healing concrete carries its own repair tools right inside the mix, waiting to work only when a crack appears. In tests and real projects, it can seal the finest lines, usually no wider than about 1/32 of an inch, and bring the surface back to its watertight state. There are 2 main ways this happens. The first is natural, something regular concrete already does a little on its own. It's called autogenous healing. When tiny cracks form and moisture enters, some leftover binder reacts again and makes new crystals that slowly close the gap. It's a weak effect, but it works on the tiniest lines. The second is more deliberate, called autonomous healing.
You need bacteria that can survive the harsh environment of concrete.
In this case, engineers add something special into the mix. Tiny helpers that only wake up when a crack forms. They can be living like certain bacteria or purely chemical. They stay inactive until water enters. Then they react and block the opening so water can't pass through. The principle is simple. Imagine a pinhole in a garden hose. You don't replace the whole hose, you just need that tiny leak to stop. The same logic drives self-healing concrete. In lab tests, engineers don't just look at cracks under a microscope. They measure how fast water moves through a sample before and after healing. When the water flow drops, the crack has truly sealed. Inside this broad idea, engineers use 3 main tricks. One depends on tiny microbes that make natural stone when they wake up.
You need bacteria that can survive the harsh environment of concrete.
Another uses microcapsules, minute beads that burst open when a crack passes through them, releasing a sealing liquid. The third uses networks of thin tubes that work like veins, carrying a liquid that can refill cracks again and again. Each method works differently, but they all chase the same result. When a hairline opens, something solid forms inside and closes it off before water can move through. The microbial path is most common. The mix holds microscopic spores tucked inside protective carriers. Those spores can sit dormant for years. When a new crack opens and water reaches them, they wake up, feed on a small nutrient stored with them, and produce limestone, a natural stone that grows right inside the gap. The new mineral bridges the 2 sides of the crack and hardens there.
If you have cracks, water comes through. If this water gets to the steel reinforcements, if they corrode...
It's a quiet, natural process that has been proven in lab and field trials for more than a decade. There's a small grain that shelters the spores through mixing and curing. It keeps them safe until water eventually enters. This grain is called a carrier. The food the spores need to make limestone is called a precursor. It's often a calcium-rich compound that travels in the same grain. When the area dries, they go back to sleep. The effect is local. Only the part that's cracked and wet seals up. The rest of the structure stays unchanged. How wide a crack can this method close? That depends on many small details. How much of the healing agent was added, how close those carriers sit to the new crack, how long it stays damp, and how warm it is.
At the start, we came back almost every 2-3 weeks to see how the process was going.
Still, most studies agree on a simple range. Cracks about as wide as a credit card's edge can be sealed fully. In mild, damp environments, you can see the mineral bridge form in a week or 2. In colder or drier air, it may take longer. The microbes like conditions above freezing. The second method, the microcapsule route, is purely mechanical. Picture a batch of wet concrete filled with thousands of microscopic beads, each containing a drop of repair liquid. When the concrete sets, those beads are scattered everywhere inside. If a crack slices through the hardened material, it cuts through some of the beads too. The pressure makes them pop, releasing the liquid right into the fresh gap. The liquid reacts with the concrete around it and hardens into a gel or solid, blocking water and even gluing the sides slightly together. The most common liquid used for this purpose is sodium silicate, a thin glass-forming solution. When it meets the wet, high pH environment inside concrete, it turns into a gel that later hardens into a mineral-like plug. Other designs use two different liquids that react when they meet, much like a two-part epoxy glue. The microcapsules themselves come in many forms. Some have polymer shells, others are made from brittle minerals. This capsule method has one big advantage: coverage. Because the beads spread evenly through the mix, any potential crack line has a good chance of crossing a few of them. But there are trade-offs. The beads must stay stable for years without leaking or drying out. They need to survive the violent spinning and grinding of mixing, but still be weak enough to break on cue later. The third method is the vascular network approach, inspired by nature. Imagine the branching veins of a leaf hidden inside a slab. Here, engineers embed a web of hair-thin tubes filled with a liquid that can harden when exposed to air or moisture. When a crack cuts across one of those tubes, the liquid seeps out, flows into the opening, and sets, plugging it. The best part is that you can refill the system later. If new cracks form, the liquid can be pumped back in through the same tiny channels. That repeat function makes this version ideal for structures meant to last decades. There are trade-offs, though. The tubes must not weaken the concrete, and the liquid must not set too soon inside them or too late in the crack. Engineers solve these issues by shaping the tube grid so it doesn't line up with high-stress zones, designing valves that allow flushing, and tuning the liquid's viscosity so it travels far but still hardens at the right moment. No matter which method is used, researchers test one thing above all: can the crack still leak? A sealed surface that still passes water is a fake success, so scientists use both visual and flow tests. They measure how much water passes under pressure and how fast dry concrete soaks up moisture by capillary action. If water movement slows, the healing worked.
It will not dissolve during the mixing, but only at the case when the concrete cracks and water gets in, it will become active.
Another quick check uses electrical resistivity, since wet, open pores conduct current better than dry, sealed ones. When resistivity rises after healing, it means the surface has dried and tightened. The limits of these systems are just as important as their strengths. They can't close a split you can stick a coin into. Wider cracks may seal on the surface but stay open underneath. That's why structural design still aims to keep cracks narrow through good reinforcement and mix control. Self-healing is a safety net, not a replacement for smart design. Knowing how it works is one thing, but is it worth the money? The real payoff of self-healing concrete.
And then he asked me if it would be possible to use bacteria to make concrete self-healing.
When people think about concrete that repairs itself, the question that always follows is whether it makes financial sense. Every owner who builds or renovates anything eventually has to face the same three realities: how much it costs to build, how much it costs to keep working, and how long it will last before something leaks or cracks. At the start, the cost is higher. There's no way around that. The materials or treatments that give concrete its self-healing behavior still carry a premium. The price can be about double that of a regular mix, depending on the job and method. That sounds steep until you remember every new material starts this way. The first projects always pay for supply chains to mature. Once more builders use it, the price drops. But for now, it's fair to plan for a clear premium up front. The real question isn't what it costs today, but what it costs across its life. A wall, slab, or deck doesn't stop spending money once it's poured. Over decades, owners keep paying for coating, patching, and sealing. Life cycle costing, an approach used in every serious construction budget, adds all of that up. The first build, every repair, every recoat, every hour of downtime. It looks at the long run instead of the first invoice. When you do that math, self-healing concrete starts to look less like a luxury and more like insurance. Standard concrete starts cheap, but keeps calling you back for work. Concrete with coatings or membranes lasts longer, but needs recoating every few years. The self-healing version starts high but keeps quiet later. The cost curve flattens because fewer leaks mean fewer trips back. Over 30 to 100 years, the line that once sat higher often ends up lower. Most of the money for building maintenance doesn't come from big failures. It comes from little leaks that force you to react, pools forming on decks, watermarks creeping along ceilings, corrosion starting at hairlines. In the UK and across Europe, almost half of all construction spending goes to maintenance and repair. Also, labor and materials always get more expensive, and a repair 20 years from now will cost far more than it does today. Money isn't the only measure. Cement is one of the biggest industrial sources of carbon, so every new yard of concrete carries a heavy footprint from the start.
If you remember how much concrete we make, the amount of cement that we need to make that concrete contributes somewhere between.
What most people forget is that the damage from leaks multiplies that footprint. Each repair needs new cement, more transport, and creates extra waste. The real question isn't how green the first pour is, it's how much carbon the structure uses to stay standing.
Innovation in both cement production and carbon utilization is absolutely necessary.
The best way to see that is to measure carbon per year of service. If a wall or deck lasts twice as long before needing a fix, its original carbon cost gets spread across twice as many years. Each year then carries less weight. Studies that look at self-healing concrete use the same method, and they all reach the same conclusion. When this material actually reduces repairs, its total environmental impact goes down, even after including the small footprint of the healing agents. The reason is simple. Repairs burn a lot of energy. Each recoating or injection job means fuel for equipment, new materials, and truck trips that all produce emissions. Skip a few of those repair cycles, and the carbon savings add up fast. The benefit grows even more when the mix also uses less cement to begin with.
Now, to make concrete, you mix cement with stone, sand, and other ingredients.
For example, when part of it is replaced with fly ash or slag. That change alone cuts emissions early, while the self-healing effect prevents extra emissions later. Some research tracks more than just carbon.
Use this calcium and carbon dioxide to precipitate calcite, and you can see that the crack is being healed by the bacteria.
It looks at total energy use, water use, and waste. The outcome is always the same. Repeated work causes the biggest impact. Once you cut out those repeat cycles, everything drops. Energy use, material use, waste, and noise from construction. Steel plays a part too. In concrete that has to stay watertight or resist corrosion, designers often add extra rebar to control cracking. If the mix can seal its own tiny cracks, that extra crack control steel can sometimes be reduced without hurting durability.
If you have cracks, water comes through. If this water gets to the steel reinforcements, if they corrode,
We've seen why it matters. Now let's head to the job site and see how it's really made. What it's like to work with self-repairing concrete. At a ready-mix plant, the self-healing ingredient looks ordinary. It comes in paper bags filled with a fine, dry powder. Workers handle it just like cement or fly ash, measuring it by weight. For new concrete, the amount added is usually between 1% and 4% of the Portland cement part of the mix.
And to make cement, you burn limestone with other ingredients in a kiln at very high temperature.
Most plants use around 7 to 13 pounds for every cubic yard of concrete. There are two simple ways to add it. The first is at the batching stage, right into the mixer with the sand and stone. That's the easiest method if the crew can safely reach the mixer. The second method is to add it at the truck stage. If safety rules or the plant layout don't allow access to the main mixer, the additive can be poured straight into the drum when the fresh concrete is loaded. The drum is spun fast for about 3 minutes before leaving the plant and turned slowly during the drive. When the truck reaches the job site, it is spun fast again for another 3 minutes before pouring. The mix itself doesn't feel strange to work with. At normal doses, there's little to no change in flow or early strength. It looks, moves, and sets the same as regular concrete. Still, every plant runs the usual tests on trial batches: slump, 3-day strength, 7-day strength, and 28-day strength, to make sure everything lines up with what they expect. Storage is simple too. The bags only need to stay dry, in a cool, ventilated place, and below 104 degrees Fahrenheit. Each bag normally weighs about 55 pounds, and smaller bags are available for smaller pours. The shelf life is 1 year from the date of manufacture, so plants just manage it like their other materials. There's one small note in the instructions for plants that use blended cement. If the cement already contains a lot of extra materials like slag or fly ash, the manufacturer recommends that at least half the cement content stays as clinker. If that's not possible, then they advise slightly reducing the additive dose and doing a quick test first. The additive doesn't change how the hoses, chutes, or vibrators are used. It also works fine with the same water reducers and retarders that plants already use.
Scientists believe that if they cured concrete with CO2 instead of water, it would be more durable.
Finishing and curing follow the usual process too. The only goal is to keep the surface from drying too quickly so the concrete strengthens evenly. After that, the self-healing part just sits inside the concrete waiting. It stays inactive until the day it's needed. Then the reaction starts automatically. For crews on site, there's no new training, no special finishing step, and no new curing process. There's another version of the product made for horizontal surfaces that are already built, like decks, balconies, pavements, and roofs. This one isn't mixed in. It's sprayed on after the concrete is hardened. It comes as two dry powders called A and B. Workers mix them separately with water right before use. For small batches, 5 liters of hot water are mixed with the A powder, and 2.5 liters of warm water are mixed with the B powder. For large jobs, those same ratios simply double to 10 and 5 liters. Once mixed, the liquid stays usable for about 3 hours, long enough for a steady work shift, but not so long that it sits idle. The spraying process is very straightforward. Each worker has 2 pressurized sprayers, one filled with A and one with B. The concrete surface needs to be clean, slightly damp or dry, and free of any leaks at the moment of application. For crack repair, they spray A directly into the crack, let it soak in, and then spray B over the same spot within a few minutes. For covering an entire deck or slab, they fog A across the full surface, wait briefly, and then fog B on top of it. Cleanup after spraying is simple. After about 24 hours, the light gel that forms on the surface can be rinsed away with clean water. No scrubbing required. The instructions do warn against using antibacterial cleaners during that rinse because they can interfere with the reaction happening inside the concrete. Another thing to note is that treated surfaces can be slippery until they're rinsed, so crews rope off the area just as they would for any coating or sealer. After application, the treated surface needs a few weeks of care. For about 6 weeks, it must stay slightly damp so the reaction inside can continue. It doesn't need to be soaked, just kept from drying out completely. If rain or humidity isn't enough, crews can mist the area or cover it with curing sheets. The temperature range should stay between 50 and 104 degrees Fahrenheit during that time. In hot weather, it's best to schedule the job for early morning or late afternoon, when the surface can stay cooler and shaded. It's different from the care regular concrete needs to cure well. Speed on site is another common question. A test by one of the suppliers showed that a trained crew with 2 sprayers can cover about 500 square meters, roughly 5,400 square feet per hour. That means an entire medium-sized parking deck or balcony area can be treated in a single day, leaving time for cleanup and inspection. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.